Okay, let's remember the definition for conditional probability. The probability of B, given that A occurs, is equal to the product of the intersection, A intersect B. Of course, it doesn't matter what order we write, A intersect B or B intersect A, divided by the probability of the given. So probability of A. Now, multiply both sides of this equation by probability of A to clear out the fractions. Okay, this is going to give us the probability of B given A times probability of A equal to the probability of the intersection. This is known as the product rule for conditional probabilities. Probability of A intersect B is equal to, this should be an equal sign right here, the probability of B given A multiplied by the probability of the given, probability of A. Okay, now let's use this in a problem. So let's suppose we have a class in which 65% of the students are female, 40% of the males, and 28% of the females are engineering majors. We are going to create what is known as a probability tree that encompasses all the given information. Okay, so we know that in our class 65% are female, and therefore we know the percentage of males as well. Now, if 65% of the students are female, what is the probability of a randomly selected student being a female? Remember, our probability is a number between 0 and 1, so this will be 0.65. So we just rewrite that percentage as a decimal. Okay, so we can put that on our probability tree. Now, if 65% are females, how many are males? Well, we're just going to subtract from 1 or from 100%. So the probability of a randomly selected student being a male will be 1 minus 0.65, which is 0.35. In other words, 35% of our students are males. Okay. Now, of the females, how many are engineering majors? We'll let E represent the engineering majors. Okay, so we know that 28% of the females are engineering majors, and so if we subtract 0.28 from 1, that will give us 0.72. So that means 0.72, or 72% of them will be non-engineers. Of the men, 40% were engineers, so that gives us a probability of 0.40. Again, we subtract from 1 to get the probability of the complement. So for our complement, we'll get 0.60. Now, what we need to do is realize what these numbers were that we wrote on the tree. Each of these numbers represents a probability. Let's write down exactly what they are. Okay, so the 0.65 is the probability of F. What is the 0.28? Well, that 28%, that this 0.28 is referring to, that's just the females. So this is equal to the probability of E given F. Here, the 0.72 is the probability of E complement given F. In other words, our tree, if we're branching out from the F in the tree, that means being female is given. We're only talking about the females. The males have no relevance to these numbers. Okay, let's continue to fill out our tree. So here we have the probability of M, which you could also call F complement. Here the 0.40. This refers to the probability that a person is engineer given that the person is male. So that's E given M. Here we have E complement given M. Sorry, running out of room there. Okay, now how do we work a problem with this using the product rule? Well, we want to figure out the probability that a student is female and also an engineering major. So that means F intersect E. According to our product rule, this will be the probability of F multiplied by the probability of E given F. Remember, the probability that we're multiplying by here is the probability of the given. So, in other words, these two match. Okay, so what are those from our tree? Well, where's the probability of F? Right here. Probability of E given F will be here. So we can just multiply along the tree to get our answer. So we take the 0.65 times the 0.28, which gives us 0.182. So once you get the hang of making a probability tree, you probably won't be needing to write P of E given F everywhere, because you'll just realize that's what it means. What you'll do when you need to find the probability of F intersect E, you will find the branch of the tree that goes through both F and E. What's the only way to get through both F and E? To go right along here, F and then E. So we follow that branch, we just multiply those numbers along, and that gives us our 0.182. And we end up using that product rule for probabilities without even realizing we're using it. We're just looking at our probability tree. Let's do another one. Let's use the same tree, but this time let's look at the probability of a randomly selected student being both a male and a non-engineering major. Okay, so this time we want probability of M intersect E complement. Okay, so now we need to find the section of the tree that goes through both M and E complement. Okay, so here's M, here's E complement. So we're going to have to go through there. And so that tells us what we're going to end up needing. Okay, so we get 0.35 times 0.60, and that gives me 0.21. All we did was multiply along the tree. Let's do another one. Let's suppose that we have a box that contains 4 white marbles and 3 red marbles, and we're going to draw 2 in succession without replacement. What's the probability of drawing a red on the second draw? let's set up our tree. On the first draw, we're going to let W1 represent getting a white marble, and R1 represent getting a red marble. And from each of those, after we draw the first marble, then we can either get white or red, which I'll call W2 and R2. I'm putting the subscripts because, for example, it's asking us to draw the probability of drawing a red marble on the second draw. Drawing a red marble on the second draw is not the same thing as drawing a red on the first. And so I don't want to call them both R because they're really two different events. So I'm calling them R1 for red on the first, R2 for red on the second. We just don't want to use the same letter to represent two different things. So let's draw a little sketch of our box. At the beginning, we start out with 4 white marbles and 3 red ones. Okay, so at the very beginning, what's the probability of drawing a white marble? Well, we have 7 marbles, 4 are white, so we end up with 4 sevens. And then we end up with 3 sevens for getting a red on the first. Now, to fill out the rest of the tree, look at the top halves first. Let's assume we got white on the first. In other words, W1 has happened for sure. So if W1 has happened for sure, we drew the white out. It says we did not replace it. That's very important. And so now one of these is gone. So now how many marbles are left? 6. How many are white? 3. So 3 6 is our probability of getting a white, and therefore 3 6 for getting a red. Now you could simplify those, but I usually just leave them. It's often nice if all the denominators match when you're doing the calculations. So I'm going to leave them. Now we move to the bottom half of the tree, and we assume that red was drawn on the first draw. So now let's put this white marble back. And now what's happened? Now we drew a red on the first, so now one of these are gone. So now we have 6 marbles, 4 are white. So 4 6 for W2, and then 2 6 for R2. Hopefully that makes sense. Okay, once we have the tree set up, now we can calculate our probability. We want to find the probability of getting R2, red on the second draw. And actually there's 2 ways that this can happen. We can either get that while getting white on the first draw. So W1 intersect R2. Remember, the intersect represents and. Or we can get red on the first and also red on the second. So these are the things that can happen. Usually I wouldn't write that. Usually I would just think about the tree. I would look at the tree and I would ask myself, well, what are the ways that I can get a red marble on the second draw? Well, here's one way, is to go through W1 to get to R2. That's not the only way. Okay, and we want these. So we can go through W1 or we can go through R1. So we're going to multiply along those 2 branches of the tree, and we're going to add them up. So we're going to get 4 6. Whoops, I'm sorry. Make that 4 7s. Times 3 6. That's the first branch. And then the second way will be to do 3 7s times 2 6. So we add this up. This is 12 over 42 plus 6 over 42. So 18 over 42, which is 3 7s. Okay, let's do another one. Okay, we have a camera, and it's manufactured in 3 locations, which we're going to call plants A, B, and C. It tells us what percentages of the cameras are made by each of the manufacturing plants, and it also gives us percentages of the cameras from each plant that are defective. And we're being asked what the probability is that a randomly selected camera is defective. So first we want to make a probability tree that summarizes everything that is in our problem. So we know information about A, B, and C. Okay, in other words, do we know probabilities when you're trying to decide what to put in the first layer of your tree? You need to ask yourself, do I have probabilities that I can put here? In other words, do I know the probability of a randomly selected camera being from A? Well, yes, I do, because A manufactures 45% of the cameras. So 0.45. And for B, we get 0.3. And for C, we get 0.25. And what do all these add up to? What should they all add up to? They should add up to 1. And they do. Now for each of these, the cameras they make will either be defective or non-defective. Okay. Defective or non-defective, D complement for each of them. And we should be able to assign probabilities to each of these. Okay, so 1.5% of the cameras produced by plant A are defective. So that means 0.015. So how many are non-defective? You would take 1 minus 0.015, which is 0.985. All the branches that leave a point in your tree should add up to 1. Okay, now we move to B. We know that 2% of the cameras are defective, so 0.02, which leaves us 0.98 for the non-defective ones. And then for C, 2.75% are defective, so 0.0275. Subtract from 1 to get 0.9725. Okay, we want to figure out the probability that a randomly selected camera is defective. So we want P of D. Now what we need to do is we need to find all the branches that lead to D. Where are they? Well, here's one branch that leads to D. We're going to multiply along there. Here's another way to get to D. Multiply along there. And here is a third way to get to D. So we're going to multiply along all of those branches, and we're going to add them all up. So 0.45 times 0.015 plus 0.30 times 0.02 plus 0.25 times 0.0275. So punch all this into your calculator, add them all up, 0.019625. That's our answer. Let's do one more example. Let's suppose that we have a box with 8 batteries. We know 2 of these are defective. We're going to choose one randomly, one at a time, not replace it, and then we're going to keep testing it until a non-defective one is found. And then we're going to figure out the probability of various numbers of batteries tested. So what we need to do before we can start doing any kind of calculation is draw a probability tree to describe our situation. So our layers of our tree, we have the first draw, and then we'll have the second draw, and then we'll keep going if we need more. So on the first draw, what can we get? We can either get a defective battery or a non-defective battery. Okay, if we get a defective battery, what's the probability that that happens? Well, our box has 8 batteries, 2 are defective. So 2 out of 8 are defective, therefore 6 out of 8 are good. So now what happens if we get a defective battery on the first draw? Well, we draw again. If we draw again, what can happen? We can either get a defective battery or a good battery, right? Now, what if we get, on the first draw, what if we get a non-defective battery? What happens? Well, we stop. It says we're going to keep drawing them until we get a non-defective one. If we get a non-defective one, we're not going to do anything else. So this branch of our tree right here just stops. Okay, so assuming we got a defective the first time, what's the probability we get a defective now? Well, we drew one out. We did not replace it. So if there were 8 in the beginning, how many are there now? Well, now there's only 7. So that'll be our denominator. How many of those are bad? Well, there were 2 defective ones. We drew one. In other words, here we have 2 defective ones. Therefore, we have to have 6 good ones. So one of the defective ones is now gone. So 1 out of 7 is defective, and therefore 6 out of 7 are good. Okay, now what happens if we get a defective one on the second draw? Well, we draw again, right? And what can we get? Defective or not defective. And what if we get a non-defective or a good one on the second draw? Well, then once again we stop, right? Okay, so let's fill out our probabilities. What's the probability of getting a defective one on the third draw? Well, that means we got a defective on the first, defective on the second. Ooh, so those 2 are both gone. Ooh, what's the probability of getting a third defective battery? 0, because there are not 3 defective batteries in the original box. There's only 2, so it's not possible to get 3 defective batteries. So that we get a 0 probability there, and if you're alert, you won't even draw that branch. And then what's the probability of getting a non-defective one on the third draw? 1. That's what we call a certain event. Getting a defective one on the third draw is what we call an impossible event. The probability is 0. So, again, here we stop once we get that non-defective battery. So now we need to figure out the answers to our questions. Let's let X be the number of batteries drawn. I'm introducing this other variable so that we can just be able to write things in a clear way with correct notation. So we're going to call this probability of X equals 1. Okay, we call that a random variable when it represents a number, and yes, it is acceptable notation to put X equals 1 here in parentheses like this. And so I guess this would be our answer to part A. So if we drew just one battery, that means we must have gotten a good battery on the very first try. So that means we ended up here. Okay. So that looks like that probability then is 6/8 or 3/4. Final answer, so we should simplify it. The probability of drawing 2 batteries, this means we're going to stop after the second draw. So we're going to have to multiply along the tree here to here, and then we had to stop. So here this is going to be 2/8 times 6/7, which is 6/28, which is 3/14. Okay. Now getting 3. Okay, where are we going to be in this case? Okay, that means we must be going here, and then here, and then here, because we need to get to where we stop after the third draw. So we multiply along that branch of the tree, so we get 2/8 times 1/7. Sorry. 2/8 times 1/7 times 1 is what we want. Not sure why that's working. Let's start over. 2/8 times 1/7 times 1. Okay, this is going to be 1/28. Sorry about that. I think I have a bad spot in my screen. Anyway, hopefully that helps you to understand